So unit operations are where the physical forces predominate, those treatment methodologies we call as the unit operations, and where chemical and biological reactions are involved, so those are referred as unit processes. So we have discussed already in this session what are the treatment methodologies that are adopted in a conventional water treatment plant. So we were discussing about the aeration. So objectives of aeration is to remove the taste and odor, which will increase the DO, removes the hydrogen sulfide and the odor, carbon dioxide, and converts iron and manganese from soluble to insoluble state, and also mixes the chemicals with the water. And we have discussed how, depending on the saturation value, gas desorption and the gas absorption takes place, which obeying the Henry's law. So factors affecting the exchange of these gases we have discussed. It is mainly the area of interface, thickness of the interlayers, time of contact, the partial pressure of gases, and the degree of the saturation value that is underlying over the gas in the water. And to ensure proper aeration, to increase the area of water contact with the air, to keep the surface of the liquid constantly agitated so that we can increase the rate of gas exchange, to increase the time of water contact with the air, we can increase the time of flow. And we have discussed that the aerators can be classified based on the two mechanisms, where the water droplets or the thin films of water will be brought in contact with the atmosphere, and the another mechanism where the small bubbles of air which will going to rise in the water. So based on this mechanism, the aerators, we have many aerators. So we were discussing about the cascade aerator. So the cascade aerator, where we will going to provide a number of steps so that the water can able to flow in the form of a thin film, and depending on the raw water characteristics, we can decide its design criteria. So usually the number of steps that are provided will be 4 to 6. The head requirement will vary from 0.5 to 3 meters, and the space requirement is about 0.015 to 0.045 meters square per meter cube hour. And the gas removal efficiency of this cascade aerator, it is about 20 to 45%. It can able to remove the carbon dioxide, and to the maximum of about 35% hydrogen sulfide can be removed with this cascade aerator. Another type of aerator is multiple tray aerator, as you are seeing in this schematic representation, where we will going to have a number of trays which are placed at certain spacings. So the coke or ceramic will be placed in these trays, which are having a size of about 50 to 150 mm. The number of trays and the spacing will usually vary from 4 to 9 trays, with a spacing of about 300 to 750 millimeter, and the total height of this multiple tray aerator will vary from 1 to 3 meters. And the space requirement for this is 0.013 to 0.042 meter square per meter cube hour. But the gas removal efficiency is high in this multiple tray aerator when compared to cascade, because of the providing the coke, we are increasing the surface area of exchange of the gases. So we can observe 65 to 90% carbon dioxide removal and 60 to 70% hydrogen sulfide removal. So coming to the spray aerators, where water will be made to come in contact into air in the form of a fine droplets. So depending on the size of the nozzles, the diameter of this droplets will going to vary. So the nozzle's diameter usually vary from 10 to 40 mm, which are spaced at 0.5 to 1 meter, and the pressure head at the nozzle will be usually about 7 meter. But in practice, we will vary it from 2 to 9 meters. and the discharge rating per nozzle is around 18 to 36 meter cube per hour, and the aerator area will be about 0.03 to 0.09 meter square per meter cube per hour. And the gas removal efficiency in this spray aerator is about 70 to 80% carbon dioxide, and 90 to 99% hydrogen sulfide can be removed. And in this, the time of exposure of the droplets to the air, we can calculate using this formula where T equals to 2CV square root of 2H by G into sine X, where H is the total head of water available at the nozzle, and CV is the coefficient of velocity, and X is the angle of inclination of nozzle. Okay. So next type is the diffused aerator, where the air bubbles will be made to rise in the water, which is most commonly followed in the wastewater treatment. And next is the mechanical aerator, which is also commonly used in the wastewater treatment. So coming to the advantages of the aeration, so mainly it is used to remove the iron and manganese at the varied concentration. So what is the necessity to remove the iron and manganese? Because concentration of 0.3 milligram per liter, it will going to cause yellow to reddish brown stains on the plumbing fixtures. And also, if the concentration exceeds 1 milligram per liter, it will going to impart the metallic taste to the water, and at the same time, the water looks turbid. Okay, so not only that, even we can able to remove the hydrogen sulfide from this aeration. So the reactions that takes place when we do the aeration is the hydrogen sulfide, when it reacts with oxygen, it forms the water and releases the elemental sulfur. So aeration is most effective method to remove the hydrogen sulfide when it has a concentration less than or it is lower than 2 milligram per liter. So the limitation of this aeration is it requires significant head of water for it efficient working, and at the same time, if we do more aeration, because of increase of the DO, the water will become more corrosive. Okay, and at the same time, for removal of taste and odor when we do the aeration, so it won't be much effective when it is at a higher concentration. Okay, so along with the carbon dioxide or some adsorption process, it will be efficient. And at the same time, we may require the additional lime to neutralize this carbon dioxide, because in the further process, because in the water treatment, when we go for the lime treatment, so in such cases, by doing this aeration, we have removed most of the carbon dioxide. So for further miscellaneous treatment, we may need the additional lime. So coming to the next treatment methodology, that is the sedimentation. It is nothing but the process of removal of suspended particles through the gravitational settling. So here, depending on the nature of the suspended solids, we can go for the plain sedimentation, or we can have sedimentation with coagulation. Okay, so in this sedimentation process, as the particles will going to settle, so this depending on the nature of the particles and its settling velocity, we can observe the various types of settling. So it can be of these four types: discrete settling, flocculent settling, the hindered settling, and the compression settling. So here, the first type of settling, that is the discrete settling, it mainly follows the Stokes law, where the particle diameter will be less than 0.1 mm. Okay, so that settling velocity of those discrete particles can be calculated based on the Stokes law, which is expressed in the form of the equation as shown here. So which is mainly depends on the specific gravity of the solids and the kinematic viscosity. Okay, so this is a schematic sketch which represents the various types of settling in a sedimentation column. So as I told you, the type 1, that is the discrete particle settling, where the discrete particles will be present in the dilute suspension, whereas the type 2, the flocculent settling, where the flocculent particles will be present in the dilute suspension, and in this, the particles will come closer or coalesce with each other. And the hindered settling, it is the settling that occurs between the flocculant and the compressed, where the intermediate concentration of the flocculant particles we can able to observe. And the compressed settling, here it is a type of settling where the particles that are of high concentrations will going to settle due to the compression that the upper particles takes place, because of the weight of the upper particles. So that's why it has referred as the compression settling. So there are various types of sedimentation tanks that can be used in the water treatment. So depending on the nature of the flow, we can say as fill and draw type or intermittent type, and the another one is the continuous type. Okay, this is the schematic sketch showing the fill and draw type, where the water will be taken into a tank, it will be filled, and after providing the treatment, then it will be taken out. So that's why it has referred as the fill and draw type. And the another type is the continuous type, where the water will be continuously taken into the sedimentation tank, and after the treatment, the effluent is taken out of the tank continuously. So here the inlet and the outlet are separated with the by providing the baffles between these two. The design aspects of the sedimentation tank, so it mainly depends the velocity of flow, capacity of the tank, inlet and the outlet arrangement that we are having, the shape of the tank, and the other miscellaneous considerations. So the first foremost, the capacity of the tank, it can be determined by two methods. Depending, first one is either based on the detention period or based on the overflow rate. So the detention period, it is the theoretical time taken by the particle of water to pass between the entry and exit of the settling tank. Okay, so capacity of the tank we can decide based on the rate of flow of water and the detention time. So here the rate of flow of water into detention time will gives us the capacity of the tank. The another method where the overflow rate is used. Overflow rate is nothing but the quantity of water passing per unit hour per unit area of the settling tank. Okay, it is also referred as SOR, surface overflow rate. So we know that according to the above relation, so we can write the detention time T equals to C by Q, where C is the capacity of the tank, and we know the capacity can be calculated length into breadth into depth of the tank divided by the flow rate. And the detention time can also be calculated using this relation T equals to distance of the descent of particle by the velocity of descent. So distance of descent of the particle is nothing but the depth of the tank, and the velocity of the descent is the rate of settling of that particle. So D by V, so that we can write as side water depth. Okay, SWD is side water depth by the surface overflow rate. So with this relation, when we equate these two equations, then we will get the side surface overflow rate is equal to volume, that is equal to Q by LB. Okay, so this shows that the sedimentation of the particle is independent of the depth of the tank. Okay, it is nowhere related with the depth of the tank. So for the plain sedimentation, we will take the surface overflow rate as 40 to 50 meter cube per meter square hour. And for sedimentation with coagulation, we will take 50 to 60 meter cube per meter square hour. So coming to the shapes of the tank, the most commonly used shapes are rectangular tanks with the horizontal flow, circular tanks with the radial or spiral flow, and hopper bottom tanks with the vertical flow. Okay, so these are the schematic sketches which are representing these two, the rectangular and the circular. So the hopper bottom tank with the vertical flow is this. So as we reviewed the previous GATE question paper, so most of the problems were asked on this sedimentation. So I have taken one such example. The surface overflow rate of a primary settling tank is 20,000 liter per meter square per day, and its kinematic viscosity of water in the tank is 1.01 into 10 to the power of minus 2 centimeters square per second. And specific gravity of that particle is 2.64. Acceleration due to gravity is 9.81, and the minimum diameter of the particle that will be removed with the 80% efficiency in the tank we need to calculate. Okay, so they have actually the answer is 14.46. So let us know how they have calculated this. So according to this numerical, the efficiency is 80%, which can be calculated based on the US, that is the surface overflow rate, by the settling velocity. So surface overflow rate into this, whatever the efficiency, so 0.8 into 20,000 into, since 20,000 liters they have given, so we need to convert it into meter cube. So I have multiplied 10 to the power minus 3, and we need to express in terms of second. So I have divided by 60 into 60 into 24, that is 86,400. So we will get the as 1.85 into 10 to the power minus 4 meter per second. So, and also we know, according to the Stokes law, we can write this US equals to G minus 1 into GD square by 18V, where G is corresponds to the specific gravity of the solid and D is the diameter of the particle. So we know all this. So based on this surface overflow rate and the acceleration due to gravity, its specific gravity, so we need to calculate the diameter of the particle. So D square. So when we simplify this, we will get the diameter as 1.446 into 10 to the power of minus 5 meters. So since in the problem they asked us to express in terms of micrometer, so it is nothing but 14.46 micrometer. So one more example. So consider a primary sedimentation tank in the water treatment with the surface overflow rate as 40, and the diameter of the spherical particle removal efficiency is 90%. And they have also given to assume the density of water, the particle specific gravity, and the kinematic viscosity, which is almost similar to the previous example. So in this, the answer is B, that is 22.58. So here, only thing, the efficiency is changed. In the previous, they have given as 80. In this, it is given as 90. So based on this calculation, we will get the diameter of the particle as 22.58 micrometer. So coming to the next example, a water supply board is responsible for treating 1,500 meter cube per day of water. A settling column analysis indicates that an overflow rate of 20 meter per day will produce satisfactory removal for a depth of about 3.1 meter. And it is decided to have the two circular settling tanks in parallel. So what is the required diameter of the settling tank? Okay, we need to calculate the diameter of that sedimentation tank, and the solutions, they have given the 4 solutions. We need to identify the correct one. Okay, so actual answer is C, that is 6.91. So how? Let us know. So we know the total area of the settling tank, that is A equals to Q by V. So that is 1,500 is the flow rate and the overflow rate is 20. So we will get the surface area 75. Since the number of tanks that we need to provide is 2, okay, it is given there in that numerical. So the area of each tank will be 75 by 2, that is 37.5 meters square. And it is the circular tanks that we need to provide. So once we know the area, we can calculate its diameter. We know area of the circular tank, pi d square by 4. So we know the area. So d will be square root of area into 4 by pi. So we get the value as 6.91. That is the answer. So the next example on this, the two identically sized primary sedimentation tanks which receives water for type 1 settling under the laminar flow conditions. Okay, whenever you have type 1 settling under laminar flow condition, so the Stokes law will go into the settling velocity is according to the Stokes law. So the surface overflow rate maintained in the two tanks are 30 meter cube per meter square day and 15 meter cube per meter square day. The lowest diameters of the particles which shall be shuttled out completely under this SORs are 30 and are designated as D30 and D15 respectively. So the ratio of D30 to D15 we need to calculate. Okay, it is a very simple. The ratio value is 1.41. Okay, how? As I told you, it is according to the Stokes law, it is applicable. And in this Stokes law, the settling velocity is directly proportional to the square of the diameter. Okay. So since in this case, we have the two diameters, so we can write that as d square, that is of 30, and d square of 50. And it also given that the surface overflow rate is 30 and 15. So when we take the ratio, the value is 2. Okay, so when we take out this square root, that is square root of 2, we will get that is 1.41. So that is the answer, the ratio D30 by D15. So next is the tube settler and the laminar plates. Okay, usually in the sedimentation tanks, so it is a bit advanced technique that are being followed nowadays to increase the rate of settling of the particles. So the water flows up through these slanted tubes, which are usually placed in the inclined fashion. Either it may be tubes or it may be the plates. The flock settles out in the tubes or the plates, and as it goes on settling, it will going to drifts back down into the lower portion of the sedimentation basin. So the clarified water will going to come up through those tubes or the plates. So it is as shown in this schematic sketches. So this is the tubes, the laminar tubes. This is the laminar plates. You can observe here. So the flocks that will get settled over the lower part of the plates, as it gets crowded, it will going to drifts back to the lower portion of the sedimentation tank, and only the clear water will going to come up of that plate or the tubes. So next is the constituent of coagulation sedimentation tank. Suppose if we are not having the plain sedimentation, if the turbidity of that water is more, then there will be necessity of adding the coagulant. Okay, so then we call that as coagulation sedimentation tank. So the important constituents or the components of this are the feeding devices, mixing device, the flocculation tank, and then comes the sedimentation tank. So the coagulants that are generally used to destabilize those colloidal particles, we call those chemicals as the coagulants. And the process of adding the coagulants is known as coagulation. So with this addition of the coagulant, we can able to destabilize the colloidal particles which are negatively charged, and also the fine particles we can able to remove. Okay, so initial aggregation of this destabilization of particles will takes place due to the addition of this coagulants. And the common coagulants that are being used in the water treatment are the aluminum sulfate, commonly known as alum, then the chlorinated copperas, which is nothing but the mixture of the ferrous sulfate and the ferric chloride. Then the ferrous sulfate and lime can also be used as the coagulants, even the magnesium carbonate and the sodium aluminate. So coming to the principle of this coagulation, actually it involves the two steps. One is the flock formation, and next is the electric charge neutralization. Okay, so with this, there will be destabilization of the colloidal particles will takes place. Okay, this destabilization will takes place in the 4 steps. So first is the double layer compression. Okay, as you see in the schematic sketch, so negatively charged are the colloidal particles. So because of the addition of the coagulants, the whatever the hydroxides that are formed are all uh, positive in nature. So that will going to surround the negatively charged colloidal particles. So there will be formation of the double layer. And because of the variations in the charges that it possesses, the charge neutralization will takes place. Okay, and then the bridging will going to happen between these particles, so it will get attached to each other, and then the colloidal entrapment will takes place. So it will going to attach each to one each other, so that it will start growing in a bigger size. Okay, and in this, to determine the optimum dosage of the coagulant, the test that we perform is the jar test. So using the jar test, using the 6 jars with the 1 liter of sample each, and by adding the varying dosage of the coagulant into these beakers, and by mixing thoroughly for 1 minute and then slowing down the mixing to 30 rpm for about 10 minutes, and then we need to check the final turbidity to know which dose is effective. Okay, so the dose which has the minimum retention of the turbidity, so that is considered as the optimum dose. So here, let us take one problem on this about the alum dosage. So a surface water treatment plant operates round the clock with a flow rate of 35 meter cube per minute. The water temperature is 15 degrees centigrade, and the jar testing indicated an alum dosage of 25 milligram per liter with the flocculation at GT value of 4 into 10 to the power of 4, producing optimal results. So alum quantity required for 30 days for the operation of the plant, we need to calculate. Okay, they have asked us to calculate in kgs. Okay, so here what they will going to do is they will going to give the additional data to confuse you. Okay, actually in this particular problem, we are not need of either the temperature or the GT value. Okay, so we need only the total flow rate and the dosage of the alum. So the solutions they have given are 4 solutions they have given. So the answer is kg of alum is required to treat that quantity of water in that water treatment plant. So how? Let us know. So we know the flow rate is 35 meter cube per minute. Okay. So to convert that to per day, so we are multiplying 60 into 24. So we will get 50, sorry, 2 meter cube per second, we have divided it. So we will get 50.4 into 10 to the power of minus 6. And the alum dosage is 25 milligram per liter. So alum quantity required for 30 days, to calculate that, whatever the flow rate into the quantity alum dosage, that is 25, it is expressed in terms of milligrams. To convert into kg, we have multiplied 10 to the power of minus 6. So that is, this is for 1 day. For 30 days, we have multiplied 30. So we will get the answer as 37,800 kg. So the answer is C, 37,800 kg of alum is required. So coming to the coagulants feeding, it can be done in 2 ways, dry feeding and wet feeding. Okay, so toothed wheel and the helical screw is used for the dry feeding, whereas the conical plug float method and the adjustable weir and float are used for the wet feeding. And the mixing devices that are used in the water treatment are either we can use the compressed air, the hydraulic jump method, the mixing channel, and the mixing basin with the baffle valves, and mixing basin with the mechanical means. Okay, so the last two are the one which are most commonly used in the water treatment plants whenever we are treating on a large scale. So the flocculator, so this is a very important operation, we can say, where the whatever the coagulant flocks that are formed, the precipitate of the coagulant that are formed, to increase its size, we have to provide the gentle agitation, okay, which we also call as the slow mixing, okay. The gentle agitation to agitate the destabilized particles so that it can form or it can grow the flocks into bigger size. So for this, the power required is calculated using this relation P equals to half CD rho into AP into VR, where, and it can also be written as G equals to square root of P by mu V, where CD is known as the coefficient of drag of the paddles, and VR is the relative velocity of the paddles in fluid, and AP is the area of the paddles, and G is the mean velocity gradient, and V is the flocculator volume, and mu represents the absolute viscosity. Okay, so based on this, we can calculate the power required for the flocculator. So coming to the design criteria of this flocculator, it mainly the depth of this flocculator will be about 3 to 4.5 meters. Okay, detention time will be 10 to 40 minutes. So usually 30 minutes we will going to provide. The velocity of the flow is 0.2 to 0.8 meter per second, and the area, total area of the paddle will be 10 to 25% of the cross-sectional area of the tank. Then the peripheral velocity is vary from 0.2 to 0.6 meter per second. So you have to keep in mind this peripheral velocity should be less than 1 meter per second. So velocity gradient is 10 to 75 per second, and GT value will vary from 10 to the power of 4 to 10 to the power of 5, and the power consumption will be about 10 to 36 kilowatts per mld of water. The outlet velocity of this flocculator usually vary from 0.15 to 0.25 meter per second. The CD value depends on the shape of the blade. So most commonly used will be the flat blades. So it is about 1.8. The distance between the paddle edge and the side of the basin is 15 to 40 centimeters. And the K value, the constant is 0.25. The relative velocity is 75% of the paddle velocity, and the area of the paddle will be length of the blades, width, and the number of blades in that compartment that we have provided. And the distance between the two paddles in the same compartment will be about 1 meter. So there is one common problem on this flocculation, that is the calculation of the power requirement. So I have taken one such example. A flocculation tank consists of 1,800 meter cube of water, which is mixed using the paddles at an average velocity gradient of 100 per second. The water temperature and the corresponding dynamic viscosity are 30 and 0.798 into 10 to the power of minus 3 Newton Siemens per meter square respectively, and the Newton seconds per meter square. The theoretical power required we need to calculate. Okay, so according to the calculation, we will get the value as 14.364. Okay, these are the problems which will be asked for about 2 marks. So the power required we can calculate using the relation P equals to mu into V into G square. Okay, in this we 0.798 is given, that is the dynamic viscosity, and 1,800 is the water, and G is the velocity gradient, that is 100. So when substituting that, when we simplify, we will get in terms of Newton meter per second, and that is converted to kilowatts. So it is 14.364 kilowatts. So coming to the filtration. So filtration, as you all know, that it is the process of passing the water through the beds of sand for so that whatever the remaining can be removed. And two common types of filters that is being used in the water treatments plants are the slow sand filter and the rapid sand filter. So, and one more type, that is the pressure filter, is also being used, but generally it will be used in the swimming pools. So whatever may be the type of filtration units, but the mechanism will remain the same. So the filtration mechanism mainly consists of the mechanical straining, flocculation and sedimentation, and the biological metabolism and electrolytic changes. Okay, that means when we pass the water through the filter, there will be the small pores. So these suspended solids which are present in that water will be held up over those filter media, so which is referred as the mechanical straining. And as the finer particles will get into those pores, and those within those pores, okay, those small pores which are present in the filter media will act as the sedimentation tank. Okay, so there the finer particles will get settled over those. So that's why the second step we call as the flocculation and sedimentation. And the third one is the biological metabolism. Okay, you know that the water will always contain microorganisms. So the at the filter bed, or at the surface of the filter bed, there will be a biological slime or a layer will going to form. So that will going to act on those microorganisms, will act on the organic matter that are present in the influent of that filter. So there will be removal of such organic substances takes place. And at the same time, the electrolytic changes, the sand will be usually positive charged, and the colloidal which has escaped from the sedimentation tank will contain, will possess charge neutralization, or the electrolytic changes will takes place. So though these are the four steps that are involved in the filtration process. So coming to the filter material, as you know that most commonly used filter material is sand, which should be free from the dirt, uniform in size and nature, and it should be hard and resistant. And the most important, it should not lose more than 5% of its weight after immersing or after living in hydrochloric acid for 24 hours. And its density, the gravel that is being used in the next layer, it should have a density of about 1600 kg per meter cube. And sometimes we can also use the anthracite or anthrafilt in the as a filtration media. So these types of the filters can be classified based on the two factors. One is the rate of filtration. The other one is based on whether the flow is gravity or under pressure. So based on the rate of filtration, we say it is slow sand filter and rapid sand filter and the pressure filter. Whereas based on the gravity, so we call that as the gravity filter. So the examples are the slow sand filter and the gravity filter. Whereas in the pressure filter, we are going to pass the water under pressure so that we can have a large rate of filtration. So that is referred as the pressure filters. So this is the schematic showing the how the construction of the slow sand will be. So slow sand filter mainly consists of the enclosure tank. There will be inlet chamber, and in the center part of that slow sand filter, there will be the filter media, that is the sand and gravel, and the last compartment will be the outlet where we will going to have the outlet pipe of this slow sand filter. Okay, and it mainly consists of the enclosure tank, the filter media, as I told you, the base materials, under drainage system, inlet outlet arrangement, and the other apprentices. So here the slow sand filter, the bed slope will be usually 1 in 100, or it can vary up to 200. The depth will be of about 2.5 to 3.5 meters, and the media sand layer that we provide, the depth will vary from about 600 to 900 and the effective size of that sand will be 0.2 to 0.4, and the uniformity coefficient is 1.8. Remember this effective size of the slow sand filter is 0.2 to 0.4, and the uniformity coefficient is 1.8 or 2.5 to 3. Okay, this is again the same thing, how the various layers are provided in the slow sand filters of the various thickness. And the filter head in this slow sand filter will be limited to zero point 0.7 to 1.2. And the cleaning of the slow sand filter is not done by backwash, just by scraping the upper layer. So about 1.5 to 3 centimeter of the top sand will be removed. So this is when there is head loss is observed. And here the whatever the biological layer that will be formed over the surface, so it is referred as Schmidt's decay. Okay, that is dirty skin, and the rate of filtration of this slow sand filter is less, that is about 100 to 200 liters per hour per meter square. But since the size of the sand that we are using is small in this slow sand filter, the bacterial removal efficiency is up to 98 to 99%. Okay, so this is the schematic of the rapid sand filter. The depth of this tank will be about 2.5 to 3.5 meters, area 10 to 80 meters square, and the number of units that we need to decide depending on the quantity of the quantity of the water that we need to treat. Okay, that can be calculated using this Wallace equation. N equals to 1.22 into square root of Q, where Q will be substituted in terms of MLD. And coming to the filter media, the sand layers will be of about 60 to 90 centimeter in depth. Effective size is 0.35 to 0.55, and the uniformity coefficient is 1.3 to 1.7. Whereas the base material, that is the gravel, is again 60 to 90 centimeter in depth. 5 to 6 layers of each of 10 to 15 centimeter depth is used, and the coarsest gravel will have the size about 20 to 40 mm. Intermediate will be vary 12 to 20 or 6 to 12, and the finest gravel will be 3 to 6 mm. And the under drainage system, okay, this is one type of filter which has a very good under drainage system. The main objective is to collect the filtered water, and at the same time also to distribute the water uniformly when we backwash that filter. Okay, this is the schematic representing the under drainage system. And the other apprentices that are used in this rapid sand filter are the wash water troughs, air compressor, and the flow control devices. And the usual operation we have in this rapid sand filter, when we it will pass through the filter media, and the treated water will be collected in the under drainage system, which will be which will be flowed at the outlet to the next treatment unit. Okay, and the most important feature of this is the filter is the backwashing. So here the backwash, when the head loss is more, we will go for the backwashing. Usually during the monsoon season, the backwash will be done at least once in a day, depending on the water characteristics. And here, while doing the backwashing, we need to first pass the air so that we can loosen up that sand particles, and then we will allow the water to rise in the sand media. And during this backwashing, about 2 to 4% of the filtered water will be used. Okay, the filtered water will be used for the backwashing. So while backwashing, we will allow the first is we will make the air to pass so that we will loosen up the media here, and then we will allow the water to flow up, and the backwashed water will be collected in the backwasher troughs, which are placed at the upper part of this sand media, and then it will be taken to the backwash drains. Okay, here the air will be passed at the rate of 1 to 1.5 meter cube per minute per meter square for about 2 to 3 minutes. Okay, so that is the important aspect that you have to remember regarding the backwashing. So coming to the numerical related with this filtration. So filtration is also one of the important unit operation on which you will going to get lot of fills. A water treatment plant of capacity 1 meter cube per second has a filter box of dimension 6 by 10 meter. Okay, the loading rate of filter is 120 meter cube per day per meter square. So when the two filters are out of service for backwashing, so what is the loading rate that we need to calculate? Okay, so in this, the answer is D, that is 144. So how? Let us know. So the total water that is being filtered is 24 into 3600, that is in a day, because it is given in terms of meter cube per second, 1 meter cube per second. So 1 into 24 into 3600. So we will get 86,400 meter cube per day. And the surface area of that filter is, it's given that the loading rate, the loading rate, we will get the surface area as 720 meters square. So area of the one filter will be equal to, they have given the dimension, so it is 60 meters square. So the total number of the filters will be 720 by 60, that is totally 12 filters. Okay, so out of this 12 filters, as they have given in the statement, the two filters are out of service for the backwashing. Means two filters will be kept for as a standby during the services, and only 10 filters will be in the operations. So then the surface area of the filters will be, one filter area is 60 meters square, then the 10 filters area will be totally 600 meters square. Then the loading rate will be whatever the total quantity of water that we need to treat divided by the area. So that is 86,400 by 600. It is 144 meter cube per day per meter square. Okay. So let us take the another example. A rapid sand filter comprising a number of filter beds is required to produce 99 mld of potable water. Consider the water loss during backwashing as the 5%, the rate of filtration as 6 meter per hour, and the length to width ratio of the filter is taken as 1.35. The width of each filter bed is to be kept equal to 5.2 meter, and one additional filter bed is to be provided to take care of the breakdown, repair, or the maintenance. So total number of filters that is required will be how much they have asked. Okay, so they have given the 4 options. So the answer is C, that is 21. Total water to be filtered, first we need to calculate. So we know 99 mld, and the since we need to also consider that 5%. So that's why we have considered this. And along with that, we say it is 103.95 mld, that is the total water. And the length to breadth ratio is given as 1.35, and width is 5.2 meters. So the length will be 7.02. Okay, and the surface area of the each filter is 36.504, and the total surface area required, we can calculate the discharge through the filter per the rate of filtration. So that is nothing but 103.95 into 10 cube by 6 by 24. So we will get the area as 721.875 meters square. Okay. So the total number of working units will be, to calculate that, the total surface area divided by the surface area of the each filter. So we will get as 19.77. Okay, so that corresponds to around 20. Okay, so actually we will going to get around 20 point something, so that is rounded up as 21. So when we compare this rapid sand filter and the slow sand filter, okay, So the important parameters or the properties with respect to rapid sand filter and the slow sand filters are the rate of filtration. Please keep it in mind. So it is 3,000 to 6,000, whereas it is 100 to 200. And the sand size 0.35 to 0.55. And here it is 0.2 to 0.3. And the most important, the bacterial removal efficiency, slow sand filter is high, about 99.9 to 99.99, whereas it is 80 to 90% in rapid sand filter. So the pressure filters where water will be passed under a pressure of about 300 to 700 kilonewton per meter square, so which is usually greater than the atmospheric pressure, and these are generally used in the swimming pools. So coming to the disinfection of water, it is the process of killing the pathogenic organisms. The substances or the materials which are used for the disinfection are referred as the disinfectants. And as you all aware that whenever we want to select the disinfectant, the important properties that we have to see is it should leave the residual concentration. It should be effective in killing all pathogenic organisms, should be harmless, economic, easily available, and unobjectionable, and the strength can be easily determined, and no personal skilled personnel is required, and also no costly equipment is needed for the application, and it should react within a reasonable time. And the various methods of the disinfection you all know. Okay, so I will directly go to the mechanism of this disinfection. So the four steps that takes place during this disinfection, one is the damage to cell wall. So initially, the whatever the chemical that we add as a disinfectant will damage the cell wall of that microorganism. Due to that, there will be whatever the cell fluid is there, so that alteration will takes place. So that is the alteration of the cell permeability and the changing the colloidal nature of the cell protoplasm, that in turn changes the fluid property of that cell, and in turn that will inactivate the enzymes that are present in those cell protoplasm, that reduces the metabolic activity of that microbe. Okay, so like this, in these four steps, the disinfection action will takes place. So in this disinfection, the most important is the disinfection kinetics. So when a single unit of microorganism is exposed to a disinfectant, the reduction of microorganisms will going to follow the first order reaction. Okay, according to that, we can express that as dN by dt, that is equal to minus Kn, where when we simplify this, we can write that as n equals to n naught into exponential of minus kt, which is known as the Chick's law. Okay, according to this, n is the number of organism and n naught is the initial number of organism that is present when before the disinfection process, and K is the disinfection constant, which depends on the nature of the disinfectant, and T is the contact time. Okay, using this kinetic, we can able to know how the action of that disinfectant will takes place on the microbes. So the important factors that affect the disinfection process are the type, condition, concentration, and the distribution of organism, type and concentration of the disinfectant that we are applying, chemical and the physical characteristic of the water that we are going to treat, the contact time that we are giving, and the most important is temperature. Okay, so here we are just focused on the chlorination. I will just tell the two important reactions. The water, when the chlorine is added to the water, it will react at the when the pH is more than 5, and it will forms hydrochloric acid and the hypochlorous acid. So this hypochlorous acid is unstable in nature. It will again disintegrate to form hydrogen ions and the hypochlorite ions. Okay, so the chlorine which has a disinfecting action are, one is the elemental chlorine, that is Cl2, other one is the hypochlorous acid HOCl, and the next one is the hypochlorite ion, that is OCl minus. Okay, so the forms by which the chlorine is applied I have just listed here. the forms of the chlorinations, at what are all the stages that we can able to add in the water treatment. Based on that, we can say as plain, pre, post, double chlorination, breakpoint chlorination, superchlorination, and dechlorination. And in the water treatment, to know the chlorine demand of the water, we will be using the concept of breakpoint chlorination. So the test for the residual chlorine that are usually conducted in all water treatment plants are listed here. So in these, orthotolidine, DPD test, chlorotex test, and the starch iodide test. So most common is the starch iodide test. So one example on this disinfection. So again, I want to repeat here on the disinfection also the most numericals are asked. So one such example I have taken. The water purification works handles 50,000 meter cube per day, which consumes about 20 kg per day of chlorine. The residual chlorine after the 15 minutes of contact time is zero point 0.2 milligram per liter. So we have to know what is the chlorine dose that is used in the treatment. So in this, the answer is B, that is 0.6 milligram per liter. So how we have calculated? So the chlorine demand will be whatever the chlorine that is being consumed, 20 kg per day. Okay, so that I have expressed by multiplying 10 to the power of 6. I have expressed in terms of milligrams. Then the flow quantity of water that is being treated, so it is given in terms of meter cube. I have expressed by multiplying 1000. So the quantity of the chlorine that is being added divided by the flow of water, we will get the chlorine demand as 0.4 milligram per liter. And they have also given after certain contact time, it is giving a residual concentration of 0.2. So that is also we need to add along with the uh, chlorine demand. So the total chlorine dose will be chlorine demand plus residual chlorine, that is 0.4 plus 0.2, 0.6 milligram per liter. So the next example here, the chlorine is used as a disinfectant in a municipal water treatment plant. It achieves 50% of the disinfection efficiency, and which is measured in terms of killing of the indicator organism in 3 minutes. And the minimum time required to achieve is 99% disinfection efficiency would be how much we need to calculate the time required, okay, to achieve the 99%. So according to this Chick's law, based on this Chick's law, so we can, based on, initially they have given the 50%. So if we assuming that 50%, that is efficiency as 0.5, so we can simplify this Chick's law and we can calculate the K value. Then using that K value, next we can calculate what is the time required to achieve the 99% efficiency. Okay, then we will get the time as 19.93 minutes. So similar, one more example. So in this 99% kill of the microorganism has been achieved. So at what time they have asked directly. Okay, in the previous, first you need to calculate the K value and then you need to calculate the time of exposure. Here directly they have given, you need to just substitute those values and calculate the time of exposure. It is 20.022 minutes. Okay, and they have also asked here the volume length of the tank. Okay, so for that, volume of the tank is equal to Q into T. So flow rate is given as 36 meter cube per hour. So we need to convert into a minute by dividing by 60. Since the time is in terms of 20.022 minute, so we will get the volume as 12.012 meter cube. Then the length will be volume by depth into width. Okay, they have also given the width and the depth. So we can able to calculate the length. So that is 8.0089. Another simple question they may ask this about the sequence of the water treatment plant. The potable water is prepared from the turbid water by They have given the 4 options for the sequence of water treatment to treat the turbid water. You need to identify the correct one. So the correct sequence, as you have already just now you have dealt with, so it will, if it is turbid water, then it will be started with the coagulation, flocculation, sedimentation, filtration, disinfection, and then it will go for the storage. So the answer is A. Okay, so let's have a look at the water requirement. So just I will show you the important water requirements for different uses. So here, depending on the purpose for which we will be using the water, the degree of the purity will going to vary. And as we all know that drinking water will need the highest purity water. So based on this, for what purpose we are using the water, the CPCB has developed the concept of designated best use. Okay, according to the CPCB, out of the several uses of water for the various purposes, the use which demands the highest quality is termed as the designated best use. And it has given those 5 designated best uses, and it which will help the managers, quality managers, and the planners to set the water quality targets and the design in the restoration of the water bodies. And also, the Bureau of Indian Standards recommended the water quality parameters for the different uses in the standards IS 2296 in the year 1992. So according to the CPCB, the designated best uses of water is classified 5. So class A, class B, class C, class D. Class A is mainly the for drinking water source without the conventional treatment but with disinfection. B is which is designated for the outdoor bathing, and C is the drinking water source after the conventional treatment with disinfection. D is propagation for the wildlife and the fisheries, and E is irrigation and the control waste disposal. So according to the various classes, the water quality parameters values are listed here. And here, the most important, the guidelines given by the CPCB to evaluate the irrigation water quality. So the most important parameters, they have given the sodium, electrical conductivity, sodium absorption ratio, and the residual sodium carbonate. Okay, based on these particular parameter values, we can decide whether that water can be suited for the which comes under the which particular class as excellent, good, medium, or bad. So coming to the water distribution, the requirements of the good water distribution, it should not get deteriorate the water quality during the distribution, and it should be capable of supplying water at all the places with sufficient pressure, should be capable of supplying the requisite amount of water during firefighting, and the layout should be such that no consumer should be without the water supply, and all distribution pipes should be preferably laid at 1 meter away or above the sewer line, and it should be watertight. Okay, the methods of distribution are generally 3: gravity, pumping, and the combined, depending on the nature or the location of that particular layout or the site. So we can adopt any of these 3. So coming to the distribution, layout of the distribution, there are 4 different types of pipe networks. So it is dead end system, radial system, gridiron system, and the ring system. Dead end system, it is suitable for the old towns or the cities which having no definite particular pattern. Whereas the radial system, it is in this, the area will be divided into the number of zones, and based on that, we can able to pump the water from the reservoir, and the supply pipes will be laid radially. It will gives the quick service, and at the same time, the calculation of the diameter of this system will be very easy. In the grid tie system, it is suitable when the layout of the city is almost rectangular, Okay, the advantage is we can have a good circulation due to the absence of the dead ends, but the calculation of the sizes of this system is bit difficult. And the ring system, the main supply line will be laid along the peripheral roads, and the sub branches will going to come out of those main lines. Advantage is water can be supplied to any point from at least two sites. So coming to the distribution reservoirs, okay, or the storage reservoirs, which we generally call. So these are provided to absorb the hourly variations and also to maintain a constant pressure. And the location and the height of this distribution reservoirs will be mainly depending on the particular site or the locality. Two types of reservoir, surface and elevated, are used. So the most important here is how to determine the capacity of this distribution reservoirs, mainly depending on the balancing storage. Okay, it is the summation of the three important components. One is the balancing storage, so the quantity of water required to be stored in the reservoir for equalizing or balancing the fluctuation demand. The second is the breakdown storage. Okay, it is oftenly referred as the emergency storage. It is the storage preserved in order to meet the emergencies. So usually a value of about 25% of the total storage capacity, or 1.5 to 2 times the average hourly supply, will be considered. And the third component is the fire storage. Okay, so this provision will take care of the requirements that is of water that is used for extinguishing of the fires, and usually 1 to 4 persons per day is sufficient to meet the requirements. So when the reserve storage is elevated, the amount of fire reserve may be determined based on this relation R equals to F minus P into T, where R is the reserve storage, F is the fire demand, P is the reserve fire pumping capacity, and T is the duration of the fire. So based on this concept, we can able to determine the total storage capacity that is needed. So coming to the conclusion, so we have discussed in this particular session about the unit operations and the processes, water treatment, methodologies that are adopted in a conventional treatment plants, and the water requirements for the various designated use. And also we have discussed about the water distribution system. So with this, I thank you all for your patience listening. And I also want to express our sorry for the inconvenience that is caused due to the internet issue. And I wish you all the best for your exams. Thank you.
Thank you, Professor Shilpa Madam. Your excellent presentation on water quality and treatment. Now, I'll request the participants to give the feedback immediately. And also, I will request participants to watch next session, which is going to start immediately by Professor D.P. Mahesh. I will give brief introduction about D.P. Mahesh. Good afternoon. Welcome back to session 2 of day 13, K 2021, which is going to present by D.P. Mahesh. Inagilva. Oh, next one now. Oh, okay.